We're going to investigate polarization using this homemade light box. It's just a cardboard box with paper taped on the inside, white paper to make it a bit more bright inside, and a simple desk lamp twisted up and shoved inside. I turn the desk lamp on, the whole box glows, and I have these diffusing filters which I can put on top. These diffusing filters are actually just the plastic parts of some Christmas decorations, well, the box that some Christmas decorations came in. Can't leave this on for long because it does get quite hot, but that makes a very effective light box. And then I've got these polarizing filters that I can chuck on top, and we can investigate what happens with those. So that's what we're going to do. So here's my light box ready to go. Here's a polarizing filter. The light's so bright coming out of there that if I place it there, you can't even see the filter. It's that bright. But over here, you can see the filter a bit more because it's a little bit darker over here. Anyway, let's place it on the brightest part. Let's take a second polarizing filter. If I rotate the second polarizing filter around, you can see that when the two filters are 90 degrees to each other, all of a sudden, light cannot be transmitted through the two polarizing filters. Place it here, it's a bit easier to see perhaps what I'm doing. And over here, it's like magic. Now those two polarizing filters are currently at 90 degrees to each other. If I take a ruler, like this, and place it on top, doesn't have any effect. Place it underneath, doesn't have any effect. But if I place it in between the two, now all of a sudden light can be transmitted through these two filters. Okay, there you go. So you can see we've got, let's lay it down and let the camera focus. Hopefully it will focus. There we go. So we've got the two polarizing filters at 90 degrees to each other and the ruler in between them showing these beautiful pretty colors. Well, this is because this is an optically active medium which rotates the polarization plane around. It rotates it around different degrees for different wavelengths of light. So because you've got the cross filters, that means different intensities of different wavelengths get through. It depends on the thickness of the plastic. It also depends on the stress in the plastic as well. Let's just get a third polarizing filter to show you ones when we just slip a third polarizing filter in the middle. Some people call these Polaroids, but Polaroid is a brand name, so I don't call them that. So we've got our two filters, cross filters, 90 degrees to each other. Take a third filter and place it on top. No difference. Put it on the bottom. No difference. Put it in between the two. And you can see what we can do there. We can lay this down. We can have the filter, the third filter that we're rotating, at an angle 45 degrees to the other two. And now light is transmitted through the three filters. So adding an additional filter actually makes more light gets through. And this is due to resolving the electric field component so that it's parallel with the plane of polarization. And by having one at 45 degrees in between, we resolve, so we get half the intensity through the first polarizing filter, then 45 degrees. So we resolve the component that's 45 degrees, then 45 degrees to that, we resolve the component that's 45 degrees. If we didn't have the one in the middle, you get the first filter, so that's filtering out half the light, and only one plane of polarization gets through. And then 90 degrees, well, there's no component 90 degrees, which is why no light gets through. Annoyingly, you're actually seeing some reflection from up here. I'm moving my hand around above it, some reflection from my lamp. Lamps that are up high in my lab. So it's not ideal. You can see those reflections because it's a shiny polarizing filter. One of my favorite demonstrations is what happens with sellotape. So the sellotape is also an optically active medium. I'm just going to cut off a piece of this sellotape. And if I fold it on itself, you know, like when you're trying to wrap a present, it all goes wrong and you end up accidentally screwing up the sellotape. Don't throw that bit of sellotape away because it's very impressive what you can do with it. So that's just an old bundled up bit of sellotape. Possibly can't see it because lack of contrast, but there you go, old bundled up bit of sellotape. Turn the light box on. Here's my two cross-polarizing filters. Let's place the sellotape in between the two. And that is absolutely beautiful. And if we rotate the sellotape around, you see the colours change with it. So if I place one filter down there, one filter on top of it, too much reflection, you can see the different colours changing as we rotate this around. Now, when I first saw this, that was just magic to me. Absolutely fell in love with this effect. I think it's incredible. I wonder if I can zoom. There we go. So you can see there the effect I'm talking about. And if I rotate the sellotape around, you can see all the different colours. Very, very pretty. And what's happening there is that the plane of polarization is being rotated as the light passes through the sellotape in different thicknesses and different layers of it. Rotate those planes of polarization different amounts, and different amounts for different wavelengths. So then you get different intensities of different wavelengths passing through both of these polarizing filters. Oh, it's beautiful. Let's just have a look at the ruler through it when it's zoomed in. Look at that. Tell me that is not absolutely beautiful. Spectacular. I could look at this all day. And this is how LCD screens work. I mean, some of them have a diffuser with a light source underneath it. Some of them have a mirror, depends on whether they've got their own light or not. They've got a polarizing filter, just like I'm holding in my left hand here. And then there's some sort of liquid crystal, and then another polarizing filter. And the liquid crystal can have two different situations. It can either have the liquid crystal molecules arranged in a way that causes the plane of polarization to rotate around, in which case light would get through, or if you apply an electric field across the liquid crystal, then the molecules will line up. And they won't change the polarization of the light as it passes through it anymore, and so you've just got your cross filters, and so no light gets through, and it goes dark. And so that's exactly how your LCD screens work. They have this transparent electrode on both sides of the liquid crystal, where on one side the electrode is shaped the same size as the segments of the display, or the dots if you've got a dot matrix display. And you choose to put a potential on those segments or on those dots. So there's a potential difference between one electrode on one side of the liquid crystal and the other electrode on the other side. And that will cause the molecules in the liquid crystal to line up, which means they're no longer turning the plane of polarization. So we just have 90-degree polarization between the, or 90-degree difference in polarization plane between the two polarizing filters, and you get a dark spot, or a dark segment. When there's no electric field, then the liquid crystal does rotate the plane of polarization, just like the ruler does. The light goes straight through, no problem. So that's how LCD screens work. How do you get different colors on the LCD screens? Well, where you've got the different dots, you just have colored filters in front of them. It's not massively efficient, but it works. It does the job. So there we go, investigating polarization. I wonder if we should have a look at a birefringent crystal through this. So many years ago, let's turn the light box off. Many years ago, I wanted to buy a decent birefringent crystal, a bit of calcite, and the suppliers that were selling it to schools were charging hundreds for it. And I didn't have hundreds of pounds, but I found someone selling a magic healing crystal on eBay for £5. Here it is. It's not very clear, it's a bit cloudy. If I get a piece of paper like this, lay it down, let's draw a mark on this paper. There we go, mark on this paper. You can just about see through the calcite crystal. It's not wonderfully clear, but you can just about see through it if you get it in the right position. And if I rotate the crystal round, you can convince yourself that there are two images that are rotating around each other. Now, that's happening because there's different refractive indices for this crystal, for light travelling with different polarizations through it, because it's not an isotropic crystal, it's an anisotropic crystal. Essentially, we've got an optical density that's different in different directions through the crystal. And so because unpolarized light is reflecting off this paper and then passing through the crystal, we've got the polarization plane along one axis, which is being refracted by one angle, and then the one through the other axis, which is refracted through a different angle. And that gives us this sort of two refraction or birefraction effect. And I can take a polarizing filter and I can choose, might just be able to see what's going on there. It's a bit cloudy, but you might just be able to see it. Maybe if I put a light box on, that might help. You can choose which of those images, which of those optical paths to make visible, which I think is pretty spectacular. I think that's pretty special. And you could take your birefringent crystal and you could place it on a piece of polarizing, you can't see, turn the light off, piece of Polaroid like this, or polarizer like this, and you could take the second filter on top, 90 degrees to the first, so we've got cross filters just like we had before. And as we rotate the crystal around, you see the crystal goes dark, there, and then light again, then dark, then light again. So it's dark there, because the planes of polarization are in line with either the top or the bottom filter. It's light there, because the planes of polarization are 45 degrees to the two filters. So these calcite crystals can be used as polarizers as well, which is how they were originally used by the Norse explorers who made their way across the Atlantic, navigating by using the fact that light that passes through the clouds is polarized. And so even if you can't tell where the sun is, but you want to know roughly where south is, you can figure out where the sun is by rotating these crystals around and knowing what you're looking for. I'm not a Viking, so I don't know what I'm looking for. And there we go, that's a calcite crystal. That's a bonus for you to enjoy. Not quite as exciting as our what's it called? Our sellotape, but there we go. I'm just going to play now. Maybe a calcite crystal and a bit of sellotape, and you can see there's a small bit of the effect that we were looking at. If I get the two in line, you can just, it's a bit too bright, I think. With my eyes, I can just about make out different colours of the sellotape as I rotate it around. It's quite a bright light, so you can't really see it very well. It's doing the same thing as the two polarizers did, but a bit more subtle. And so, you know, what the Vikings did is they had polarized light from the clouds. Your eye is actually slightly polarized light as well. So that's, this thing here acts as your cross polarizer in the middle, your 45-degree polarizer in the middle to work out where the sun is. Very clever. I'll stop there. That's all you're getting this morning. Enjoy.